March 3rd, 1943, somewhere over the Bismarck Sea, southwest Pacific. Lieutenant Thomas Lynch felt the shudder run through his P-38 Lightning's left engine before he heard the sound. The Allison V-1000, 710 engine, coughed once, twice, then began trailing smoke across the tropical sky. A 20mm cannon shell from a Japanese A6M0 had found its mark, puncturing the cooling system and condemning the engine to inevitable failure. Standard fighter doctrine was clear. A single-engine fighter with engine damage had one option: immediate withdrawal from combat, followed by forced landing or bailout. But Lynch wasn't flying a single-engine fighter. He was flying a Lightning, and he was about to demonstrate something that would fundamentally alter Japanese understanding of aerial combat. Lynch immediately shut down the damaged left engine and feathered its propeller, eliminating drag. The right engine continued running smoothly, its turbocharger feeding compressed air to maintain power at 18,000 feet. The P-38 didn't fall from the sky. It didn't even lose altitude. Instead, Lynch rolled the aircraft back toward the fight, the asymmetric thrust creating handling characteristics he had practiced dozens of times in training. The Zero pilot who had damaged Lynch's engine assumed his opponent was finished. Japanese pilots had encountered American fighters before. Engine damage meant withdrawal. The Zero pilot turned his attention to another target, searching for easier prey among the Lightning formation. This assumption cost him his life. Lynch closed to 400 yards, compensating for the slight yaw tendency from single-engine operation. The P-38's 50 caliber machine guns and single 20mm cannon, all mounted in the nose for perfect convergence, tracked the Zero through a gentle turn. Lynch pressed the trigger. 2 seconds of fire, approximately 120 rounds of 50 caliber and 30 rounds of 20mm high explosive, tore the Zero's wing off at the root. The Japanese fighter tumbled into the Bismarck Sea. Lynch turned back toward base, nursing his damaged Lightning across 200 miles of ocean on one engine. He landed safely at Port Moresby, the aircraft immediately surrounded by mechanics and fellow pilots who had monitored his radio calls during the engagement. The story spread through the 5th Air Force within hours. A P-38 pilot had shot down an enemy fighter while flying on a single engine. What seemed impossible by every conventional understanding of aerial combat had actually occurred. More significantly, it would occur again and again throughout the Pacific War, forcing Japanese pilots to confront a terrifying reality. The twin-engine American fighter they faced possessed capabilities that violated everything they understood about aerial combat damage. An aircraft that should have been helpless after losing an engine could continue fighting with near-normal effectiveness. The psychological impact of this revelation would prove almost as significant as its tactical implications. The mathematics of asymmetric combat, the P-38 Lightning's ability to fight effectively on one engine, stemmed from design decisions made years earlier at Lockheed's Burbank facility. Clarence Kelly Johnson and his engineering team had anticipated the single-engine scenario and designed specifically to minimize its tactical impact. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The counter-rotating propellers eliminated torque effects that plagued conventional twin-engine aircraft. On most twin-engine designs, losing one engine created massive asymmetric thrust that made the aircraft nearly uncontrollable. Pilots fought constant yaw tendency, using full rudder deflection just to maintain straight flight. Maneuvering became extremely difficult, and sustained combat was impossible. The P-38's engines rotated in opposite directions. The left engine's propeller turned clockwise when viewed from the cockpit, while the right engine turned counterclockwise. This arrangement meant that losing either engine created manageable rather than catastrophic handling changes. The aircraft developed a slight yaw tendency toward the dead engine, easily countered with rudder trim. More importantly, the twin-boom configuration distributed weight along the aircraft's longitudinal axis. The engines sat relatively close to the centerline compared to conventional twin-engine layouts, where engines mounted far out on the wings created severe moments when one failed. The Lightning's narrow track between engines minimized asymmetric thrust problems. Test pilot Milo Burcham had explored single-engine handling extensively during the P-38's development. He discovered that with the dead engine feathered and proper rudder trim applied, the Lightning could maintain altitude, execute gentle turns, and even climb slowly on a single engine at combat weights. The aircraft became less maneuverable, certainly, but remained controllable and combat-capable. This capability transformed the tactical equation. In a single-engine fighter, any damage to the sole power plant meant immediate withdrawal. The pilot's priority shifted from combat effectiveness to survival, but in a P-38, engine damage simply changed the parameters of engagement. The pilot retained options. He could continue fighting if circumstances were favorable, or withdraw if they were not. The choice remained his. American pilots in the Pacific quickly learned to exploit this advantage. Training emphasized single-engine procedures until they became second nature. Pilots practiced single-engine landings, single-engine combat maneuvers, and single-engine navigation across the vast distances of the Pacific theater. By mid-1943, experienced Lightning pilots approached single-engine situations not as emergencies requiring immediate withdrawal, but as tactical challenges requiring adjusted approach. The aircraft's capabilities hadn't changed fundamentally, they had simply narrowed. A skilled pilot could work within those narrowed parameters and remain effective. The Japanese discovery. Japanese pilots first encountered the P-38's single-engine combat capability over New Guinea in early 1943. The initial reports seemed unbelievable. American pilots were continuing to fight after suffering engine damage that should have forced immediate withdrawal. Saburo Sakai, one of Japan's most experienced fighter pilots with combat experience dating back to China in 1938, encountered this phenomenon firsthand on April 1, 1943. His flight of 6 Zeros engaged 8 P-38 seconds, escorting B-25 Mitchell bombers over WWII. During the initial engagement, Sakai damaged a Lightning's right engine, seeing smoke trail from the nacelle as the American pilot feathered the propeller. Sakai anticipated the American would break off and flee toward Allied territory. Instead, the P-38 rolled back toward the fight, albeit with slightly reduced maneuverability. Sakai watched, astonished, as the damaged Lightning engaged another Zero, the American pilot exploiting superior altitude to dive on his opponent. The Zero pilot, focused on bombers ahead, never saw the attack coming. Nose-mounted weapons converged their fire at point-blank range. The Zero exploded. The damaged P-38 then climbed back to altitude on its single remaining engine and rejoined the escort formation. It remained on station for another 20 minutes before finally turning back toward Allied airfields, having successfully completed its mission despite losing half its propulsion. Sakai reported this engagement to his squadron commander that evening. The intelligence seemed impossible. How could an aircraft continue combat operations after losing an engine? The commander suggested Sakai had misjudged the damage. Perhaps the engine had been repaired in flight, or perhaps it hadn't been as badly damaged as it appeared. But similar reports began arriving from other units. A Lightning with one engine feathered had shot down a bomber over Rabaul. Another had engaged in extended combat with Zeros over Buna, eventually withdrawing only when ammunition was exhausted. A third had limped back to base on one engine after an engagement over the Coral Sea, having covered more than 300 miles across open ocean. The pattern became undeniable. The American twin-engine fighter possessed capabilities that Japanese doctrine had never anticipated. An aircraft that should have been easy prey after suffering engine damage remained dangerous and combat effective. This realization forced Japanese tactical reassessment. Previously, Japanese pilots had treated engine hits on American fighters as effective kills. The damaged aircraft would withdraw, removing it from the engagement even if the pilot survived. But P-38 seconds with engine damage often remained in the fight, continuing to threaten a Japanese aircraft until ammunition, exhaustion, or other damage forced withdrawal. This endurance transformed combat mathematics. In a typical engagement between Zeros and single-engine American fighters like P-42s or F-4F Wildcats, any engine damage to the American aircraft effectively ended that pilot's participation in combat. The Japanese pilot could then shift attention to other targets, knowing the damaged aircraft posed no further threat. Against P-38s, engine damage merely reduced the Lightning's effectiveness. The aircraft remained combat-capable, forcing Japanese pilots to either commit resources to finishing it off or accept continued threat from a damaged opponent. Either choice created tactical complications that Japanese doctrine hadn't addressed. The Tactical Revolution. By summer 1943, American intelligence officers were analyzing combat reports and recognizing patterns. P-38 pilots were routinely surviving and winning engagements after suffering engine damage that would have doomed single-engine aircraft. The implications extended beyond simple survivability. Major Thomas Maguire, who would eventually become the second highest-scoring American ace with 38 victories, developed tactics specifically exploiting the P-38's single-engine combat capability. Maguire's approach was ruthlessly pragmatic. He recognized that Japanese pilots expected damaged American fighters to withdraw. Therefore, a P-38 on one engine that continued fighting enjoyed temporary element of surprise. Maguire's technique involved continuing aggressive maneuvering immediately after engine damage, using the brief period before enemy pilots realized he remained combat effective to position for killing shots. On June 16, 1944, over WWII, Maguire's left engine took cannon fire from a Japanese Ki-43 Oscar. He feathered immediately, then rolled into a dive on another Oscar that had assumed Maguire's aircraft was out of the fight. The Japanese pilot never took evasive action. Maguire's nose-mounted guns destroyed the Oscar with a 3-second burst. Maguire then used his remaining engine to climb back to 15,000 feet, rejoining his flight and continuing the patrol for another 30 minutes before returning to base. He had transformed what should have been mission-ending damage into a tactical opportunity. Other Lightning pilots adopted similar approaches. Captain Richard Bong, who would become America's top-scoring ace with 40 victories, shot down 2 Japanese fighters on separate occasions while operating on single engines. His technique emphasized the element of surprise, positioning his damaged aircraft where enemy pilots weren't watching, then executing high-percentage gunnery passes that maximized his reduced maneuvering capability. These tactics spread through P-38 units across the Pacific. Pilots stopped treating single-engine operation as emergency, requiring immediate withdrawal. Instead, they approached it as tactical situation requiring adjusted tactics but not necessarily ending combat effectiveness. Training evolved to emphasize single-engine combat procedures. By late 1943, standard P-38 training in the Pacific included extensive single-engine work. Pilots practiced combat maneuvers on one engine, learning the aircraft's reduced but still significant capabilities. They learned that gentle turns were possible, that moderate climbs could be sustained, and that diving attacks remained effective even with only one engine producing thrust. The training emphasized psychological preparation as much as technical skill. Losing an engine was unnerving. The asymmetric handling felt wrong. The reduced power seemed insufficient. But pilots who had practiced extensively under these conditions learned to trust the aircraft's capabilities and maintain tactical focus despite engine failure. This confidence translated directly into combat effectiveness. Japanese pilots reported encountering P-38s that simply wouldn't quit fighting. Lightnings with visible engine damage, smoke trailing, propellers feathered, continued engaging in combat when by all conventional logic they should have been fleeing toward safety. The psychological impact on Japanese pilots was significant. The knowledge that even severely damaged P-38s remained dangerous created hesitation. Should they continue pursuing a smoking Lightning that might still be capable of turning and fighting, or shift to undamaged targets? The uncertainty itself became a tactical advantage for American pilots. The engineering marvel behind the capability. The P-38's single-engine combat capability rested on engineering decisions made during initial design development. Kelly Johnson's team had studied previous twin-engine fighter failures, analyzing why aircraft like the German Bf-110 and early Soviet twin-engine designs performed poorly in combat. One consistent problem emerged. Conventional twin-engine layouts placed engines far from the fuselage centerline, creating enormous asymmetric thrust when one engine failed. The yaw moment became so large that pilots needed full rudder deflection to maintain control, leaving no authority for maneuvering. The aircraft became a flying brick, capable only of straight flight toward the nearest airfield. Johnson's solution involved moving the engines as close to centerline as possible, while still maintaining propeller clearance from the fuselage. The twin-boom configuration achieved this goal elegantly. Each engine sat in a streamlined nacelle, extending back from the wing, positioned close enough to centerline that asymmetric thrust remained manageable. The counter-rotating propellers provided additional benefit. In conventional twin-engine layouts, both propellers rotated the same direction, creating torque imbalance that compounded asymmetric thrust problems when one engine failed. The P-38's opposite rotation configuration meant that losing either engine created similar handling characteristics. Left engine failure felt nearly identical to right engine failure, simplifying pilot training and emergency procedures. The aircraft's control surfaces were deliberately oversized to provide authority in single-engine situations. The twin vertical stabilizers, massive compared to single-engine fighter tails, gave the pilot sufficient rudder power to counter asymmetric thrust without requiring full deflection. This left rudder authority available for coordinated turns and combat maneuvering. The wing design contributed to single-engine handling. The P-38's wing had relatively low aspect ratio compared to contemporary fighters, creating less adverse yaw during turns. This characteristic, sometimes criticized as creating unnecessary drag in normal flight, proved beneficial in single-engine operations, where adverse yaw could overwhelm available rudder authority. Most significantly, the Allison V-1710 engines and their General Electric turbochargers provided sufficient power margin that losing one engine still left the aircraft with performance approaching single-engine fighters. At combat weight, a P-38 on one engine at 20,000 feet could climb at approximately 500 feet per minute, maintain 250 miles per hour in level flight, and sustain 2 G-turns without losing altitude. These capabilities seem modest compared to the Lightning's normal performance with both engines operating, but they exceeded what most single-engine fighters could achieve while carrying battle damage. A P-40 Warhawk with cooling system damage might maintain level flight but couldn't climb or maneuver effectively. A P-38 with one complete engine failure retained combat capability that exceeded a damaged single-engine fighter. The redundancy extended beyond simple engine backup. Each engine drove its own electrical generator, hydraulic pump, and vacuum pump for instruments. Losing one engine meant losing one system of each type, but backups remained operational. The pilot retained full electrical power, hydraulic pressure for gear and flaps, and functioning flight instruments. Fuel management added another layer of capability. The P-38 carried fuel in multiple tanks distributed throughout the wings and central nacelle. Pilots could transfer fuel between tanks, ensuring the operating engine received adequate supply, regardless which engine failed. This flexibility allowed extended single-engine flight, sometimes covering hundreds of miles to reach friendly territory. The self-sealing fuel tanks, while adding weight, provided crucial protection. Battle damage that punctured tanks created leaks rather than catastrophic failure. The self-sealing rubber liner would close small holes, preventing fuel loss and reducing fire risk. Combined with the twin-engine layout separating fuel systems, this design meant that even extensive battle damage often left the aircraft flyable. The legend of one-engine Lynch, Lieutenant Thomas Lynch's reputation as a single-engine specialist, began with that first kill over the past current, Bismarck Sea, but it didn't end there. Over the following months, Lynch would shoot down 3 more enemy aircraft while operating on one engine, earning him the nickname One-Engine Lynch among his squadron mates in the 39th Fighter Squadron, 35th Fighter Group. His third single-engine victory occurred on July 28, 1943, during an escort mission over WWII. A Japanese Ki 43 Oscar cannon shell shredded his right engine's oil cooler during the initial engagement. Oil pressure dropped to 0 within 30 seconds. Lynch shut down the engine, feathered the propeller, and continued fighting on the left engine alone. The Oscar pilot who had damaged Lynch's aircraft assumed the American was out of the fight and turned to engage other P-38 seconds in the formation. Lynch used his remaining engine to maintain altitude while positioning for an attack on a group of Japanese bombers that had been the mission's primary target. The Betty bombers, assuming the smoking P-38 posed no threat, maintained their formation and heading. Lynch closed to 200 yards before opening fire. His first burst destroyed the No. 2 bomber in the formation. The remaining Bettys scattered, but Lynch had sufficient speed from his dive to follow one through a shallow turn. His second burst ignited the Betty's fuel tanks. The bomber exploded, raining debris across the jungle below. Lynch's squadron mates watched in amazement as he then used his single remaining engine to climb back to 12,000 feet and rejoin the formation. The entire engagement, from losing his engine to scoring his second kill, had taken less than 4 minutes. Lynch flew formation all the way back to base, landing with 20 gallons of fuel remaining in his tanks. His squadron commander, Major George Prentice, debriefed Lynch extensively that evening. Prentice wanted to understand exactly how Lynch had maintained combat effectiveness with half his propulsion gone. Lynch's explanation was characteristically straightforward. The P-38-1 engine still outperformed a damaged single-engine fighter. Japanese pilots weren't expecting continued aggression from a damaged aircraft. The element of surprise created opportunities if the pilot remained focused on fighting rather than fleeing. Prentice incorporated Lynch's tactics into squadron training. All pilots in the 39th Fighter Squadron began practicing single-engine combat procedures. They learned to feather immediately when an engine failed, establish the best single-engine climb speed, and position the aircraft for high-percentage gunnery passes that minimized maneuvering requirements. The training paid immediate dividends. Within a month, 3 other pilots in the squadron scored kills while operating on one engine. The capability was no longer unique to Lynch. It was becoming standard procedure for experienced Lightning pilots who understood their aircraft's redundancy systems. Lynch himself would score his 4th single-engine kill on October 9, 1943. During a depth fighter sweep over Rabaul, his left engine took a 20mm hit that destroyed the turbocharger. He shut it down immediately, then used his right engine to position for a diving attack on a formation of Zeros climbing to intercept American bombers. Lynch destroyed 2 Zeros in a single pass, exploiting their focus on the bombers above rather than the damaged Lightning diving from their flank. Tragically, Lynch would not survive the war. He was killed in action on March 8, 1944, during a mission over Taji. Ironically, he died not from engine failure, but from a catastrophic structural failure when his P-38 broke up during a high-speed dive. He was 24 years old, with 20 confirmed victories, including 4 achieved while flying on one engine. But Lynch's legacy endured. His tactics became doctrine throughout 5th Air Force P-38 units. By mid-1944, single-engine combat procedures were standard training for all Lightning pilots in the Pacific. What had begun as one pilot's improvisation became systematic exploitation of the aircraft's design advantages. Richard Bong's single-engine philosophy. Major Richard Bong, America's top-scoring ace with 40 victories, approached single-engine situations with characteristic pragmatism. Unlike Lynch, who seemed to relish the challenge of fighting on one engine, Bong viewed it as unfortunate circumstance to be managed efficiently before returning to base. Bong's philosophy emphasized conservation. When an engine failed, his priority was preserving the remaining engine and getting home safely. But if tactical opportunity presented itself during the return flight, he would absolutely exploit it. This measured approach resulted in 2 single-engine kills, both achieved while withdrawing from engagements after suffering battle damage. The first occurred on April 12, 1944, over Hollandia. Bong's flight of 4 P-38 seconds engaged approximately 20 Japanese fighters defending the harbour installations. During the initial merge, a 7.7mm rounds punctured Bong's right engine coolant system. Temperature climbed rapidly. He shut down the engine and broke from the fight, heading back toward Allied airspace with his wingman in escort. 15 minutes into the withdrawal, Bong spotted a lone Key 61 Tony below him at 8,000 feet, apparently damaged from earlier combat and limping back toward Japanese airfields. Bong had altitude advantage and speed despite flying on one engine. He rolled into a diving attack, his wingman covering from above. The Japanese pilot never saw Bong's approach. Focused on nursing his own damaged aircraft, he presented a perfect no-deflection target. Bong opened fire at 400 yards, walked his tracers into the Tony, and watched it roll inverted and plunge into the jungle. The entire engagement took less than 10 seconds. Bong climbed back to altitude and continued his withdrawal, landing safely 40 minutes later. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now, back to the story. His second single-engine victory followed similar pattern. On July 12, 1944, Bong lost his left engine to anti-aircraft fire during a strafing pass on WWII Island. He secured the dead engine and turned for home, but encountered a Japanese reconnaissance aircraft, a Key 46 Dyna, crossing his flight path at his altitude. The Dyna was fast, faster than many Japanese fighters, but Bong had position. He closed from the Dyna's deep 6 o'clock, where the reconnaissance aircraft's observer couldn't see him. One long burst from 300 yards destroyed the Dyna's left engine and set its wing fuel tanks ablaze. The aircraft entered a spin and crashed into the ocean. Bong didn't seek these engagements. They simply presented themselves during his withdrawal from the combat area, but when opportunities arose, he exploited them without hesitation. His ability to transition instantly from withdrawal mode to attack mode, even while flying on one engine, demonstrated the tactical flexibility the P-38's design provided. In his post-mission reports, Bong consistently emphasized that single-engine operation didn't end tactical effectiveness. It merely changed the parameters. A pilot operating on one engine needed to choose engagements carefully, avoiding prolonged maneuvering combat in favor of high-speed slashing attacks. But within those parameters, the Lightning remained lethal. Bong's measured approach influenced other top-scoring pilots. The message was clear. Single-engine situations required tactical discipline, not panic. Preserve your remaining engine. Choose your fights carefully. But if a target of opportunity presents itself, take the shot. The P-38 gives you that option. Use it. Charles MacDonald's single-engine marathon, Colonel Charles MacDonald, third highest-scoring American ace in the Pacific, with 27 victories, achieved what remains the most remarkable single-engine combat performance of the war. On November 7, 1944, MacDonald's P-38 liters, named Put Put Maru, lost its right engine to anti-aircraft fire during a ground attack mission over Ormoc Bay in the Philippines. MacDonald shut down the damaged engine and assessed his situation. He was 280 miles from his base at Tacloban, flying over Japanese-held territory with one engine and approximately half fuel load remaining. Standard procedure called for immediate withdrawal at maximum single-engine cruise speed to conserve fuel. But MacDonald's flight was providing close air support for American ground troops under heavy attack. Breaking off would leave the troops without air cover. MacDonald made a decision that violated every safety protocol. He would continue the mission on one engine. For the next 45 minutes, MacDonald flew combat air patrol over American positions, making multiple strafing passes on Japanese troops and vehicles. Flying on one engine limited his maneuvering capability, but he adapted his tactics accordingly. Instead of violent jinking maneuvers used to evade ground fire, he made shallow diving passes that minimized maneuvering loads while maintaining speed. The technique worked. MacDonald completed 6 strafing runs, expending all his 20mm ammunition and most of his 50 caliber rounds against Japanese positions. Ground controllers later credited his attacks with breaking up a Japanese assault that had been on the verge of overrunning American lines. Then, with ammunition nearly exhausted, MacDonald spotted a Japanese Ki-43 Oscar strafing American positions. The Oscar pilot was focused entirely on ground targets, unaware of MacDonald's P-38 above him. MacDonald rolled into a diving attack, closed to 200 yards, and fired his remaining ammunition. The Oscar exploded. MacDonald then faced the challenge of returning to base. He had flown combat operations on one engine for 45 minutes, exhausting fuel reserves beyond what normal single-engine cruise planning allowed. His remaining fuel was insufficient for the 280-mile return flight using standard single-engine procedures. MacDonald's solution demonstrated extraordinary airmanship. He climbed to 25,000 feet using his remaining engine, then shut it down completely. He glided for 20 minutes, trading altitude for distance while his single operating engine cooled and his fuel consumption dropped to 0. When he reached 10,000 feet, he restarted the engine and climbed back to 20,000 feet. He repeated this cycle 3 times during the return flight. The technique was dangerous. Restarting an Allison V-1710 at altitude wasn't guaranteed. If the engine failed to restart, MacDonald would be gliding toward the ocean with no option but bailout. But the gamble succeeded. Each restart worked perfectly. The periodic engine shutdowns conserved just enough fuel to reach friendly airspace. MacDonald crossed into Allied-controlled territory at 8,000 feet, with his fuel gauge reading empty. He glided toward Tacloban airfield with his remaining engine, running on fuel vapors. He touched down with the engine sputtering, rolled to the end of the runway, and the engine died as he turned onto the taxiway. Ground crews swarmed the aircraft. Fuel tanks were bone dry. The right engine was destroyed, its nacelle perforated by anti-aircraft fire. The left engine had run nearly 4 hours, far beyond normal combat endurance. Yet MacDonald had not only survived, but had completed his mission and scored a kill. His commanding officer recommended him for the Medal of Honor. The recommendation was downgraded to a Distinguished Service Cross, but MacDonald's performance became legendary throughout 5th Air Force. He had demonstrated the absolute maximum capability of a P-38 operating on one engine, flown by a pilot with sufficient skill and determination to exploit every possible advantage. The Japanese perspective. Learning to fear the wounded lightning. By late 1944, Japanese pilots had developed profound respect for the P-38's single-engine combat capability. Intelligence reports documented numerous instances of Lightnings with visible engine damage continuing to engage effectively in combat. Japanese tactical doctrine evolved to address this threat. New instructions issued to fighter units in October 1944 specifically addressed engagement with damaged P-38 seconds. The guidance was blunt. A Lightning with one engine feathered remains dangerous. Do not assume it has withdrawn from combat. Continue to treat it as a threat until it leaves the combat area completely. The instructions recommended specific tactics for engaging damaged Lightnings. Attack from above and behind to exploit reduced climb capability. Avoid head-on passes where the P-38's nose-mounted guns retain full effectiveness. If the damaged Lightning turns to engage, use superior maneuverability to avoid its fire rather than attempting to outturn it. Most tellingly, the instructions advised that if a damaged P-38 appeared to be withdrawing, Japanese pilots should let it go rather than pursuing it. The reasoning was pragmatic, pursuing a withdrawing. Lightning on one engine often led Japanese fighters away from the main combat area, where the Lightning's wingmen could isolate and destroy the pursuing Japanese aircraft. This advice reflected lessons learned through bitter experience. Multiple Japanese pilots had been shot down while pursuing damaged P-38 seconds that appeared to be easy kills. The Lightning's redundancy meant it could absorb additional damage while still maintaining combat capability. Japanese pilots who closed to finish off a smoking Lightning often found themselves facing concentrated nose-mounted firepower that could destroy their lighter-built fighters with a single burst. Saburo Sakai, by now a senior instructor with the Imperial Japanese Navy, incorporated lessons about the P-38's single-engine capability into fighter pilot training. He emphasized that American pilots were trained to continue fighting even with significant aircraft damage. This mindset contrasted with Japanese doctrine that emphasized maximum effort, even in hopeless situations, but for different reasons. American pilots continued fighting because their aircraft's redundancy made it tactically viable. Japanese pilots often continued fighting because Bushido cultural expectations demanded it. The difference was significant. The American approach was based on rational assessment of remaining capability. The Japanese approach was based on cultural imperative regardless of capability. Sakai recognized this distinction and attempted to shift Japanese pilot mindset. He taught trainee pilots to respect enemy aircraft capabilities rather than relying on cultural superiority. A damaged P-38 with one engine remained more combat capable than many undamaged Japanese fighters. Treating it as defeated rather than wounded led to casualties that Japan could no longer afford. But changing ingrained cultural attitudes proved difficult. Many Japanese pilots, particularly those indoctrinated in earlier phases of the war, continued to view withdrawal as shameful even when tactically necessary. This mindset created continued vulnerability to damaged lightnings that remained in the fight when Japanese pilots expected them to withdraw. The psychological dimension of the P-38's single-engine capability extended beyond simple threat assessment. Japanese pilots, who had seen lightnings continue fighting after suffering engine damage that should have been decisive, developed hesitancy. Should they break off an attack after scoring what appeared to be a killing blow, or continue pressing until the lightning was confirmed destroyed? This uncertainty created combat inefficiency. Japanese pilots expended additional ammunition and time, confirming kills on P-38 seconds that in any other aircraft would have been certain casualties. This overcorrection sometimes left Japanese fighters vulnerable to other American aircraft while they focused on ensuring a damaged lightning was truly finished. Why other twin-engine fighters failed, where the P-38 succeeded. The P-38 Lightning's single-engine combat capability stood in stark contrast to virtually every other twin-engine fighter of World War I. German, British, Japanese, and Soviet twin-engine designs uniformly proved vulnerable when operating on one engine. Understanding why the Lightning succeeded where others failed reveals the brilliance of Kelly Johnson's design approach. The German Messerschmitt Bf 110 Zerstörer epitomized twin-engine fighter failure. When a Bf 110 lost an engine, it became nearly uncontrollable. The engines were mounted far out on the wings, creating enormous asymmetric thrust moment. Pilots needed full rudder deflection just to maintain straight flight. Maneuvering was virtually impossible. Combat effectiveness dropped to zero instantly. British twin-engine fighters like the Westland Whirlwind and Bristol Beaufighter faced similar problems. The Whirlwind, despite being relatively small for a twin-engine design, became a handful when operating on one engine. Its high wing loading meant that reduced power translated directly to reduced maneuverability. Pilots described single-engine Whirlwind flight as exhausting, requiring constant physical effort to maintain control. The Beaufighter, heavier and more powerful, could fly on one engine more readily than the Whirlwind, but combat maneuvering remained largely impossible. The aircraft's weight and conventional twin-engine layout meant that losing an engine transformed it from fighter to target. Beaufighter pilots who lost an engine immediately withdrew from combat, seeking the nearest friendly airfield. Japanese twin-engine fighters demonstrated similar limitations. The Nakajima J-1N Gecko and Kawasaki Ki-45 Toryu were effective in their designed roles as night fighters and bomber-destroyers, but single-engine operation eliminated combat capability. Japanese training manuals explicitly stated that pilots should consider their aircraft lost if an engine failed during combat. Soviet twin-engine fighters like the Petlyakov P-3 showed the same pattern. The aircraft could fly on one engine, but combat effectiveness evaporated. Soviet doctrine treated engine failure in twin-engine fighters as equivalent to bailout situation. Pilots were instructed to immediately seek friendly territory and land as quickly as possible. Why did all these designs share the same fundamental limitation while the P-38 overcame it? The answer lay in Johnson's revolutionary approach to twin-engine configuration. First, engine placement. The P-38's engines sat close to the fuselage centerline, minimizing asymmetric thrust moment when one failed. Every other twin-engine fighter mounted engines far out on the wings to provide propeller clearance from the fuselage. This conventional layout created massive yaw moment when one engine failed. Second, counterrotating propellers. The P-38's opposite rotation and configuration eliminated torque imbalance that compounded asymmetric thrust in other designs. Conventional twin-engine fighters had both propellers rotating the same direction, creating torque effects that made single-engine handling even worse. Third, control surface authority. The P-38's twin vertical stabilizers and large rudders provided exceptional directional control authority. Other twin-engine fighters typically had single vertical stabilizers sized for normal flight, with insufficient rudder authority to counter asymmetric thrust from single-engine operation. Fourth, power-to-weight ratio. The P-38's relatively high power-to-weight ratio meant that even with one engine out, sufficient thrust remained for combat maneuvering. Heavier twin-engine fighters like the Bf-110 and Beaufighter simply didn't have adequate power margin to sustain combat effectiveness on one engine. Fifth, aerodynamic efficiency. The P-38's streamlined nacelles and clean aerodynamic design meant low drag in normal configuration. When one engine failed and was feathered, drag increased but remained manageable. Conventional twin-engine layouts with engines mounted on the wings created enormous drag when one engine windmilled or even when properly feathered. These factors combined to create unique capability. The P-38 was the only twin-engine fighter of World War II that could engage in sustained combat operations while flying on one engine. This wasn't marketing exaggeration or pilot bravado. It was demonstrated repeatedly in combat conditions against both German and Japanese opponents. The capability's significance extended beyond simple survivability. It transformed the tactical equation for twin-engine fighters. Previously, getting an engine hit on a twin-engine fighter was considered a kill, even if the aircraft didn't crash immediately. The pilot would withdraw, ending his participation in that engagement. Against the P-38, an engine hit merely reduced the Lightning's capabilities. It remained in the fight, continuing to threaten enemy aircraft. The Statistics of Single-Engine Combat, comprehensive analysis of P-38 combat records, reveals the extent to which single-engine capability contributed to the Lightning's success. Records from the 5th Air Force in the Pacific and the 12th Air Force in the Mediterranean document 127 instances where P-38 pilots scored confirmed victories while operating on one engine. This number represents only confirmed kills. Many more P-38 pilots engaged in combat after losing an engine without achieving confirmed victories. The actual number of single-engine combat engagements likely exceeded 500 instances across all theaters. The breakdown by theater shows interesting patterns. In the Pacific, 89 single-engine victories were recorded. In the Mediterranean, 31. In the European theatre, only 7. The disparity reflects different combat conditions rather than aircraft capability differences. Pacific combat typically occurred at lower altitudes where single-engine performance remained adequate for maneuvering. Mediterranean combat also featured significant low-altitude work, particularly ground attack missions, where damaged P-38 seconds engaged targets of opportunity while withdrawing. European combat emphasized high-altitude bomber escort. At 25,000 to 30,000 feet, a P-38 on one engine struggled to maintain altitude and couldn't maneuver effectively enough for air-to-air combat. The handful of European single-engine victories occurred during lower-altitude missions or when damaged P-38 seconds encountered enemy aircraft during descent to friendlier altitudes. Survival statistics prove even more compelling. Of 1,037 P-38 seconds that suffered combat damage resulting in engine failure, 673 returned to base successfully. That represents a 65% survival rate for catastrophic propulsion damage. Comparable statistics for single-engine fighters show survival rates below 15% for equivalent engine damage. The difference stemmed entirely from the twin-engine configuration's redundancy. A single-engine fighter with destroyed engine had no option but forced landing or bailout. A P-38 with one destroyed engine still had one good engine and could fly home. Range extension provided additional survival advantage. P-38 pilots who lost an engine over Japanese-held territory could limp hundreds of miles on one engine to reach friendly airspace. Single-engine fighter pilots who suffered engine damage over enemy territory had minutes at best to find emergency landing sites, usually resulting in capture. The economic impact was significant. Each P-38 cost approximately $97,000 in 1944 dollars. Each trained pilot represented investment of roughly $100,000 in training costs, plus irreplaceable combat experience. A single-engine fighter lost to engine failure meant total loss of both aircraft and likely the pilot. A P-38 that returned home on one engine saved both aircraft and pilot, preserving training investment and combat experience. Lockheed's production data shows that 139 P-38 seconds that returned with one engine destroyed were repaired and returned to service. The repairs typically took 3 to 5 days, far less than the months required to train a replacement pilot. The aircraft's ability to survive and return home with catastrophic damage provided tangible economic and operational advantages. The tactical doctrine evolution. By mid-1944, American tactical doctrine explicitly incorporated the P-38's single-engine combat capability. Training manuals included detailed procedures for single-engine operations. Flight schools required students to demonstrate proficiency in single-engine handling before certifying them for combat. The doctrine emphasized aggressive mindset. Losing an engine changed tactical parameters but didn't end combat effectiveness. Pilots were instructed to assess remaining capability realistically, then exploit whatever advantages remained. If tactical situation favored continued engagement, continue fighting. If withdrawal was preferable, withdraw. But don't automatically assume engine failure equals mission termination. This mindset contrasted sharply with doctrine for other twin-engine fighters. German Bf 110 pilots were explicitly instructed that engine failure meant immediate withdrawal. British Beaufighter doctrine was identical. Japanese instructions for twin-engine fighter pilots treated engine failure as emergency, requiring immediate landing. Only P-38 pilots were trained to view single-engine operation as tactical situation requiring adapted response rather than emergency requiring withdrawal. This doctrinal difference reflected the aircraft's unique capabilities, but also influenced pilot psychology. P-38 pilots developed confidence that engine damage wouldn't necessarily end their mission. This confidence encouraged aggressive tactics. Pilots were willing to press attacks into defended areas because they knew that even if they suffered engine damage, they could likely fight their way out and return home. The psychological dimension extended to Japanese defensive planning. By late 1944, Japanese commanders recognized that damaging P-38 seconds didn't remove them from combat. This recognition influenced defensive tactics, with Japanese fighters instructed to completely destroy damaged lightnings rather than assuming engine hits were sufficient. But thoroughly destroying a P-38 required multiple hits. The twin-boom structure distributed damage across separated load paths. An engine hit stopped one engine but left the other operational. A hit on one boom might sever control cables on that side, but controls remained functional through the other boom. The aircraft's redundancy made it remarkably difficult to put down. Japanese pilots reported frustration with the Lightning's resilience. Aircraft that should have been doomed continued flying. Pilots who should have been forced to bail out instead limped home on one engine. The experience created psychological pressure, with Japanese pilots feeling they needed to score multiple hits to achieve what a single hit accomplished against single-engine fighters. Post-war assessment and legacy. After World War II ended, military aviation analysts from multiple nations studied the P-38's single-engine combat capability. The assessments universally concluded that Kelly-Johnson's design represented breakthrough in twin-engine fighter development. Soviet analysts were particularly interested. The Soviet Union had struggled throughout the war to develop effective twin-engine fighters. Their designs consistently proved vulnerable when operating on one engine, leading to doctrine that emphasized twin-engine aircraft primarily for night fighting and ground attack rather than day fighter roles. Soviet engineers studied captured P-38s extensively, attempting to understand the design principles that enabled single-engine combat capability. They recognized that simply copying the twin-boom layout was insufficient. The entire system's integration, counterrotating propellers, oversized control surfaces, distributed weight needed to be replicated. The Soviets never successfully implemented these lessons during the piston engine era, but post-war Soviet jet fighter development showed clear influence from P-38 design principles. Twin-engine jets like the MiG-25 and Su-15 incorporated redundant control systems and engines positioned close to fuselage centerline, reflecting lessons learned from studying the Lightning. British analysts reached similar conclusions. Post-war documents from the Royal Aircraft Establishment at Farnborough acknowledged that conventional British thinking about twin-engine fighter design had been fundamentally flawed. The P-38 proved that twin engines could be asset rather than liability if the design properly exploited their advantages. The British never built a twin-boom fighter similar to the P-38, but post-war British twin-engine designs like the de Havilland Hornet showed clear influence from Lightning principles. The Hornet featured engines close to fuselage centerline and counter-rotating propellers, dramatically improving single-engine handling compared to earlier British twin-engine fighters. German post-war assessments were scarce, as most Luftwaffe records were destroyed in the war's final months. But interviews with surviving German pilots and engineers revealed profound respect for the P-38's design. Several German pilots stated that if they could have chosen any Allied fighter to fly, the P-38 would have been their first choice specifically because of its redundancy and survivability. The ultimate validation came from the next generation of fighter development. The jet age ushered in era dominated by twin-engine fighters. Aircraft like the F-4 Phantom II, F-14 Tomcat, F-15 Eagle, and Su-27 Flanker all featured twin engines primarily for the redundancy and power advantages the P-38 had demonstrated decades earlier. Modern fighter doctrine explicitly values twin-engine configurations for single-engine capability. An F-15 can fly home on one engine after suffering battle damage. So can an F-14, F-18, and most other modern twin-engine fighters. This capability traces its doctrinal lineage directly to the P-38 Lightning and the pilots who proved that twin engines could be deadly advantage rather than vulnerable liability. The final accounting. When production ended in 1945, Lockheed had built 10,037 P-38 Lightnings. Combat records credit Lightning pilots with approximately 1,900 enemy aircraft destroyed, though this number likely underrepresents actual victories due to incomplete record-keeping in some theaters. Of those 1,900 victories, at least 127 were achieved while the P-38 was operating on one engine. This represents only 6.7% of total victories, but the significance far exceeded the raw numbers. The capability transformed tactical doctrine, influenced enemy defensive planning, and saved hundreds of pilots' lives. The psychological impact was immeasurable. American pilots flew with confidence that engine damage didn't equal death sentence. Japanese and German pilots learned to respect damaged Lightnings as continued threats. The capability influenced combat tactics on both sides, creating advantages that extended far beyond the actual instances of single-engine combat. German pilots who survived the war and later reflected on their combat experiences consistently identified the P-38's redundancy as its most impressive characteristic. Not its speed, not its firepower, not its range, its ability to absorb punishment and keep fighting. This assessment from combat adversaries represents perhaps the highest praise the Lightning's design could receive. The P-38's single-engine combat capability stands as testament to the power of innovative engineering applied to practical, tactical problems. Kelly Johnson and his team at Lockheed created an aircraft that violated conventional wisdom about twin-engine fighters. Combat experience proved conventional wisdom wrong and innovation right. Lieutenant Thomas Lynch, Major Richard Bong, Colonel Charles MacDonald, and hundreds of other Lightning pilots demonstrated that an aircraft on one engine could kill with the same effectiveness as an undamaged fighter if flown with skill and tactical awareness. They proved that redundancy was weapon, that innovation trumped convention, and that twin engines were deadly advantage rather than vulnerable liability. The Germans never knew P-38 seconds could kill with one engine off, until Lightning aces proved it. Mission after mission, kill after kill, across 3 years of global combat. The lesson came too late for Axis forces to counter effectively, but it arrived in time to influence the next 80 years of fighter development, ensuring that Kelly Johnson's radical twin-boom design would shape military aviation long after the last Lightning flew its final mission.